All right, so our next speaker is Dr. Bruce Rittmann, and many of you, I think, know Bruce or know of his work. If you're anywhere in the water treatment sector, you know all about it. We're really excited to have him here. He's a good colleague at Arizona State University. He's been involved in our Phosphorus Sustainability Network for a while, and last year he was the co-recipient of the Stockholm Water Prize, which is a really big deal. And he's going to buy drinks for everyone afterwards with the prize money, right, Bruce? No, he didn't say that. I just made that up. But in any case, so it's good to have Bruce here, and he's going to share some of his ideas and insights. Thank you, Bruce.
All right, just push the button. Push the button. All right. Well, good morning. Wow, a lot of people here. This is great. So thank you, Jim and Matt, for having me at the Phosphorus Forum. I've been at several, and this is a great event. Okay, so my talk title here is Minimizing P Loss, Maximizing Value, and I think by the time I get to the end, you'll for sure know why I'm using that as my title. Was that higher? Okay, thank you, Jim. Okay, so Jim mentioned the Sustainable Phosphorus Alliance. That's why we're here today. And the Sustainable Phosphorus Alliance originated out of the Sustainable Phosphorus Research Coordination Networks funded by NSF. I've been part of that from the very beginning. And SPA and the RCN before that have been very, very successful in this area. And so a lot of my talk is going to be built on some of the achievements that came through the Research Coordination Network and now SPA. And so I'm going to start this, and I'm going to organize my talk around an effort that Jim and I did in the early days of the Research Coordination Network. We were trying to get a big picture idea of the phosphorus challenge, and so he and I worked together very intensely to try to put some quantitative understanding as to what is the real problem here, and if we're going to try to solve these problems, the problem, or in this case the problems, we should know what they are and how they work together. So we worked together and came up and did this piece that was published in Future Tense in Slate. That's an online magazine on it. And so this is going to be my organizing structure for the talk, is what Jim and I did towards the beginning of the Research Coordination Network. Okay, so first thing is, what is the main driver for P sustainability? That's what we try to get to down in the future. We're not there now, of course. And first of all, it's not running out of phosphorus. We're not going to run out of phosphorus for any foreseeable time. So that's not our problem. Our problem is, in our opinion, is number one, is the impact of phosphorus discharges on water quality. Jim showed you some pictures. I'm going to show you the same picture because it's so famous here. This picture here in Canada of the one side of the lake was fertilized with phosphorus and turned green. The other side didn't. This work was done by David Schindler. I met David a few years ago. It was really neat. Anyway, so an interesting linkage here is that David Schindler was the first winner of the Stockholm Water Prize. This was in 1991, and this work was so important that he won the first Stockholm Water Prize on that. So that gives me a chance just to say a few things about the Stockholm Water Prize, which I will, but I want to point out, though, that as Jim said, and around the world, there's something like 450 hypoxic zones. So this is a really serious global problem, and it's only going to get more serious unless we do something about it. Okay, now, about the Stockholm Water Prize. So David Schindler was the first winner, and then Mark van Loosdrecht and I won it this year for our work in environmental biotechnology. So I just thought I'd show you a couple pictures of this. So that's, by the way, it was awarded by Crown Princess Victoria of Sweden, and you can probably figure out that she's the one in the middle. Yeah, and I'm on your left, and Mark van Loosdrecht is on the right. And we won this award for our work in establishing the field called environmental biotechnology. As I go through my talk today, I will point out a few things where environmental biotechnology can play a very positive role in helping us get more sustainable. We had a great time. This was the awards ceremony in the Blue Room, and then we had the royal dinner in the Gold Room, and you could see it's truly gold. Look at this, it's really a gold room. That's me and the Crown Princess and Mark. This is Mark's wife. It's my wife. He's the president of the Stockholm International Water Institute that sponsors the prize. So anyway, it was an absolutely wonderful event. ASU had a big presence there. ASU sent 9 people besides me, and to introduce the future H2O initiative to the world. Okay, now back to the main topic here. In our paper in 2013, we relied on some really wonderful work by Donna Cordell of Australia, and we adapted her work to create this rather simple global flow of phosphorus here. So, so you've got inputs, mine fertilizer, there's some weathered phosphorus naturally comes from the soils and rocks. There's a little bit of recycling of it, and you can see how the phosphorus moves into the soils, and then eventually the produce and meat, and eventually the people. And then there are these outputs here of various ways phosphorus gets out into the environment, basically into the water environment, and that's what causes all that green stuff that we saw a few slides back. All right, so you can see there are the inputs up there, and there are not very much of it ends up getting to people, 3 out of 21, but a lot of it goes into the water environment. So you can see those numbers, you add them up down there, it's 19 and 3 is 22. So most of it ends up lost into the environment, and that's what's causing the green problems. And you see I even made a little green box down there. Okay, so what we really are interested in is making those numbers at the bottom a lot smaller. A lot smaller. So when Jim and I did this, we looked at this in 3 steps. 3 steps of making those bottom line numbers a lot smaller. All right, so I'm going to start off here with organic waste. So this is about roughly 50% of the phosphorus flow ends up as organic waste. And this is the big one is animal waste, animal manures, but also there's human waste as well. So humans are a relatively small amount, animals are a big amount, but the materials are similar on this. So we're addressing organic wastes. Now the important thing to keep in mind about organic wastes and their phosphorus is organic wastes also have lots of carbon, organic carbon in it. And that means we can harvest a lot of energy, because the energy is in the carbon, and that's a benefit. Okay, so we're now going to take a look here at this, and we're going to try to focus in on how we can reduce the phosphorus flows to the environment by intercepting the animal and human waste with their organic waste with their phosphorus in them, capturing the energy and capturing the phosphorus at the same time. So we're going to get a double benefit here for that. So this is the revised diagram that we came up with all 100% of the animal food and human wastes captured and energy and phosphorus recovered. Now, of course, 100% is a little bit what you might call aspirational, but we can do very well on this. We may not get quite 100%, but we can get a lot of it. So we use the 100%. So what you can see here is we're assuming we can take these arrows that used to come down here and make them be 0. That we can actually capture all the phosphorus from it. If we do that, that really reduces the mine phosphorus required. That number is going way down. It's 48% of the original number up there. And that leaves really only one major flow going out here, and that's the one that comes from the soils and the crops, and it's 11. So that it cuts the environmental inputs by about half. So we need to do a lot better than half, but this is a big positive impact. We get about half. So how are we going to do this? Sounds good. How can we do it? And so I'm going to talk a little bit about this. Now the Research Coordination Network published a really fine paper with many authors. I'm one of them, called The Total Value of Phosphorus Recovery. It was published in Environmental Science and Technology and it addressed this issue directly of how we were going to capture the phosphorus. And so I'm going to just summarize a few highlights from this output of our research coordination network here. So first thing, where is the organic phosphorus in these streams? And so here, this is for the United States. Where is the energy, the carbon, and also the phosphorus? And you can see by numbers here, the big number, 55% in the United States of organic wastes coming through like this is from animals. So if you want to have an impact, you first start with the animals. You get the animal manures and you collect it and you extract out the energy and the phosphorus from it. There are some other big ones in here. This is people down here. You can see it's 1%. So people are important, but not really hugely important in this flow. Now, among the animals, the big ones are cattle. We have cattle for meat and we have cattle for dairy. And so there's a lot of cattle out there producing a lot of organic waste with phosphorus. So we want to first focus on the animals because that's where the big impact will be. All right. Today, in animals, only about 1% of the flow is actually being used for energy recovery. So low-hanging fruit. Okay, so how do we want to do this? So for animal waste, we want to do some form of anaerobic digestion. This is where we use anaerobic reactors and bacteria and methanogens break down the organic, complex organics into simpler things, and eventually they make methane gas, which we can recover. Well, this has been around a long time. You can trace the large-scale use of anaerobic digestion back at least 160 years, and probably longer than that. So it's been around, it's well known, it's proven. You can do it in very simple ways. You can make it sophisticated, depending on your setting here. But the key is it generates useful methane gas, CH4, essentially the same as natural gas. The difference between this methane and natural gas is that this is renewable carbon neutral methane, and natural gas, of course, is fossil, non-renewable methane. So there's a big benefit in the global climate setting for using our renewable materials. So one of the things that's a very important factor here in getting the most energy and the most phosphorus out of this is we really need to do some sorts of pre-treatment. This is something we've discovered in our research, is that these materials that come mainly out of the animals just don't fall apart, get converted into methane. And to get the most out, you need to do various pre-treatments of them. I'm not going to talk about the details of pre-treatment today, but there are a number of pre-treatment technologies out there now that can help us get a lot more energy and a lot more phosphorus out of these wastes. By the way, the pictures down there, the one on the right is a very sophisticated, fancy anaerobic digester, and the one on the left is a really simple one. So you can go from really simple like the left to really sophisticated on the right. Now, the key thing about anaerobic digestion is that it's mainly set up to make the methane to capture the energy, but when you break down the organic materials to get the energy out, you also release most of the phosphorus as phosphate. So we're putting the phosphate in a form that can be captured. So here's a picture showing this of it, and if you look at these high P, high BOD organic wastes up here, we do a conversion. We want to produce energy. That's our #1 goal. But when we do that, at the same time, we're also releasing the phosphorus, which can be separated. Now, there are a lot of technologies available for capturing the phosphorus in a useful form. I know there are some people in this room who are purveyors of this. So there are lots of ways to go, and I'm not going to spend a lot of time on that. In our group, we work a lot with the anaerobic biological treatment, releasing the phosphate, and our favorite approach for our group is to do something where we have what we call selective absorption of it, and there are several ways to do this. I'm just showing one example of this, partly because it has such nice pictures of it, but there are several technologies that are available that are based on the same principle, and that is the selective absorption of phosphate onto iron oxide solids. So here's a picture. In this particular one, they take sand grains, they coat them with iron oxide, that's shown here in the green, And then when that iron oxide is a very selective adsorbent for phosphate, and there's the phosphate it comes up there. So this is a full-scale commercial treatment system for removing phosphorus from wastewater. It's very successful. What we need to do now is take technologies like this, and we need to adapt them so they not only do they remove the phosphorus, but they recover it and we can get it off. And that's a challenge because these were not set up for that purpose. So there's some R&D that needs to be done to adapt these processes for this new job of recovering the phosphorus as well as removing it. Okay, so that is part one. Deal with the organic streams. There's lots of energy and lots of phosphorus. Now, about the other roughly 50% of the phosphorus flow that gets lost to the environment is basically off the fields, runoff from the agricultural field. So it's roughly 50%. This one is much harder to deal. It's a much harder nut to crack than dealing with the organic wastes. So here's our diagram again here on this, and we're saying, well, Jim and I said, well, let's say we can make some real progress on this. And so in this one here, here's a new diagram, same format. Now we're going to assume, again, we're recovering all the phosphorus out of the animal and other organic waste. And now we're going to reduce the erosion and other losses to the aquatic environment off the fields by 50%. And we use 50% because this is a much harder problem, much harder. So we can't assume 100%. So we're going to assume maybe we can innovate with various practices, agricultural practices and technology practices, and maybe we can get 50%. All right, so what happens is, then you can see here's the 50%. This is half of what it was on the previous slide. And that really reduces the amount of mined fertilizer that's needed. It's just 2 up there instead of, it was 7 point something in the previous slide. And if you look at what happens in the environment, now you've got a couple of zeros and a 5.5, and now the total input to the environment is much less. So this is about an 80% cut in phosphorus emitted to the aquatic environment compared to where we started in the very first slide. So this is a big thing. So how are we going to do this one? This one's hard. Well, the Research Coordination Network also dealt with this. I was on a working group, and we published very recently, last year, this paper on managing diffuse phosphorus at the source versus at the sink. So diffuse phosphorus is things that don't come through a pipe. There are things coming off the fields, through the tidal drains, off the streets in urban areas, all those things that are not normally collected and go into a treatment plant. So we published this one here. We had a really great international working team who did this. And so here is a little schematic from the paper of this. And basically, the key thing is over here on the right side. And this is the sources of the phosphorus today, where they come from. These are the diffuse sources, the things that don't come through the pipe and go to a treatment plant. And so these are where they come from here. And you can see there's a lot of them. You've got the purple ones here that are coming mainly from agriculture. You've got the orange ones that are coming from urban areas. You've got some landscaping here. And then this is a really interesting one down here, and that is the aquatic sediments. The aquatic sediments are big sinks of phosphorus, and they've been accumulating for years and years, and so they also are exchanging phosphorus with the water column, and sometimes are really important. So we call this an internal load. It's cumulative. It's a form of legacy phosphorus, and sometimes we really have to deal with this legacy phosphorus as much as what's coming in new. So for our paper, we surveyed some examples where people had really measured where the phosphorus is coming from in various lakes. So here are about 8 lakes around the world here. And the bar chart is the contribution of the total phosphorus load, and basically it's divided in 2. So you've got in the light bar, the external load. These are things that are coming from the fields or coming from the streets. And then the dark bar is the internal load. This is the recycling from the sediments. And what you can see is that the sediments range from almost all of it to almost none of it. So depending on your setting, you're going to have to either deal with sediments, or you're going to have to deal with the external loads from, say, the fields, or in many cases, both. So it's not a simple one-size-fits-all situation here. We developed this wonderful matrix. I really love this matrix. I think it's the best thing in the paper, which describes two characteristics of the phosphorus that's in these diffuse sources. Those two characteristics are whether it's particulate, tied up, for example, with soil particles, or soluble, and whether it's organic, say in animal wastes, or it's inorganic, just plain old phosphate. And you can see there's a wide spectrum on the left side of the graph. So there's a tremendous number of different sources that are mostly particulate. They're on the left side of the graph. There's not much on the right side of the graph over there. Although one of the important things is that you've got this little arrow here is anaerobic biological conversion. This is what I just talked about a few minutes ago. So when you're doing the anaerobic biological conversion, you're converting from organic to inorganic. The arrow goes up, and you're converting from mainly particulate to soluble, and that's going from left to right. So you are converting the phosphorus into forms that are easy to capture, like I described before, or if you don't capture them, now they're really mobile and much more potent in causing the problems in the aquatic environment. But anyway, you can see there's a wide range of things. So if you're over here in the particulate side and you want to capture these things, you have to somehow remove the particles on it. We developed also this little tiered system of options that we might be able to do on this, ranging from the top to the bottom. In general, things at the top are cheaper and things at the bottom are more expensive to do. Okay, so today, if you look at people who are doing phosphorus management, most of it is in those top two layers here: reducing and conserving, mitigating and remediating, mainly on the fields. So we did an international survey of this to find out what people who are at the leading edge of phosphorus management from diffuse sources today are doing, and almost all of it is there in the top two. The paper gives a bunch of examples from around the world. Now, if you take internal sources, again, this is the sediments that are recycling. Our main thing we can do here is remove it. And that realistically involves dredging, which is expensive, can be disruptive if you don't do it right. But if you really have your major source of phosphorus being those sediments, you're going to have to get them out of the water. I mean, there's really not much choice about it. And then down at the bottom here, if you really want to do everything on it, we should try to reuse and recycle the phosphorus, even from these diffuse sources. This is technologically not so easy to do, and there's no really great developed technology for it. But if we really want to achieve the purpose, we need to even get down into this bottom part of the management plan. All right, now that comes to my last topic, the third leg of the stool, diet. You remember from the last big graphic I showed you of the flows, we got about 80% removal of phosphorus. Well, we need to do better than that. And so the next thing we can do is we can require less phosphorus by producing less grain for animals. A tremendous amount of the flow of phosphorus comes in to feed the animals. And if we didn't feed so many animals, we wouldn't need so much phosphorus, and there wouldn't be so much phosphorus leakage. Well, this is a social issue. Maybe Kathleen will talk about this at lunch. We'll see. And so Jim and colleagues published a really nice paper on diet here on this. So this is another output from our RCN. And here again now is the graphic where we are recovering all the animal wastes, capturing 50% of the erosion, land runoff type of things, and we're going to cut meat consumption by 50%. So we have to feed a lot fewer animals, and we have a lot less flow of everything through the system. If we do that, then you could see these numbers in here, those flows go down. Now, of course, you don't remember the numbers from the previous graph, and I don't either, but these, these go down. These are 50%. And then you can see what happens is we need a whole lot less mined phosphorus up there at the top, and then the bottom outcome is we're down here to only a 4.5 input into the environment, which is somehow that seems like that's not right. But anyway, I wonder if that's right. I think it should be more than 80%. I think it's 90%. I may have typed it wrong. But it certainly has gone down. So, so diet. I'm not going to talk about diet other than what I just told you. That's really not my business, is diet. I know a little bit about it, but I'm not an expert in diet. But I do know that we feed a lot of animals and we have a lot of P-flow because we feed so much animals. So if we could go to some vegetarian diets, flexitarian, artificial meats and things like that, we could have a huge positive impact. And it might be enough to put us over the top in terms of reducing the phosphorus load to the environment. All right, I'm at the end. So, take-home lessons. Take-home lesson. Number one, the easiest one, the lowest hanging fruit, capture the phosphorus and the energy out of the organic waste, the animal waste, the food waste, and the human waste. This is the low-hanging fruit because we get energy and we get phosphorus at the same time. In fact, we get more resources. Our team has put together a concept we call PARENS, which stands for Profitable Agriculture Through Recovered Energy, Nutrients, and Solids, in which we were going to recover energy either as methane, that's at the top, or as hydrogen down here. I haven't talked about how we do that, but we can capture this hydrogen. You're going to capture the nutrients, nitrogen and phosphorus here, and you're going to make some valuable residual solids, and you're going to make cleaner water. And we've analyzed this technologically, and we've also analyzed it in terms of techno-economics. And this is a brief summary of the techno-economic analysis for these, and I'll just focus in on these two bars here. These are the revenues from making methane, capturing nitrogen, capturing phosphorus, and producing valuable solids that can be reused in agriculture. These are the benefits from it. The biggest one here is the energy and the natural gas. And these are the various costs of doing this: capital costs, depreciation costs, operating costs. Anyway, the point is this bar is bigger than this bar, and so there's a positive earnings before taxes in this system. So we can turn these waste, particularly agricultural, animal waste, into a mild profit center instead of being a huge, huge liability for the environment and economically for the owners of those wastes. So we think that that's quite good. Take-home lesson number two. About another 50% of the load is coming from diffuse sources. This is a hard nut to crack here. So we want to remove, and maybe we can recover the phosphorus from these diffuse sources such as runoff. This is runoff not only from agricultural fields but from urban settings here. This is technologically hard for a lot of reasons. You know, the loadings are very periodic. You know, we don't actually have control of all these materials. They aren't in pipes. But if we can do this and get maybe 50% removal and recovery, we'll be really have done a tremendous amount towards our ultimate goal of a more sustainable aquatic environment with respect to phosphorus. And again, this is the options here for those here. And then finally, to finish the job, we think, based on the mass balances we've done, is that we probably are also going to have to manage things like our diet, and we're simply going to have to produce less meat per person so that we don't have to have such a huge flow of phosphorus through the system on that. So I don't know, I'm no big expert on that here. Now this is going in the opposite direction of worldwide trends. Worldwide there's more consumption of meat, so we kind of turn the bus around. It's going to be hard to do, but it's probably what we need to do in the long run if we're really going to get to be sustainable. So with that, this is the final output. I'm repeating this here. It's what it said before. This is our sort of aspirational goal, to cut this down very small amount of P into the environment. And finally, I hope this works. We've, working with ASU experts in this, Jim and I produced a really neat animation that illustrates all of this, and I hope this works. Let's see. Here it goes. Okay, this is what it is now. We got big fat arrows. And then we're going to go to the transition, and we're going to deal with the animal and organic waste. And now we get to the final product, and you can see just one little bitty arrow. So that's the animation here for what we're doing. And that was published in the Slate article. So with that, I've come to the end. Thank you for your attention. If you have any questions, fire away. Thank you.
Thanks, Bruce. We have plenty of time for questions, so fire away.
There we go. One.
Very interesting, Bruce. Thanks for that. The trend globally around urbanization and improved sanitation makes capturing the human portion relatively easy. My question is, how are you going to reconcile sustainable animal production and grass-fed beef with free-range chickens that are trained to poop in the right place so you can catch it?
Yeah, that's a good question. And well, yeah. Well, first of all, though, if you look at the big picture, all the things that I put together, if we were to implement step 3 and produce a whole lot less animals, then there would be a whole lot less flow that way that we'd have to worry about on it. And probably you would have more of the grass-fed, grown out in the wild, not wild, in the wild, but not in CAFOs. You would have, so it become a more important issue. But then it gets to be an example of a diffuse source. And, that's a hard problem. Here there are ways in agriculture, in like row crops, where you have drainage fields, where at least you have drainage canals, and you could, in theory, intercept it. But if you're out there in open fields and the cow poops, I mean, what are you going to do? I don't know. That's a good question. I don't know.
You can catch the pee, but you can't catch the energy when it's a diffuse.
Right. Okay. That's a good point. Yeah. So that's one of the reasons why the second step is so much harder, because you're really going to have a hard time capturing the energy out of it. So you don't get that economic and energy benefit from it. That's one of the reasons it's technologically much more difficult. If you got everything captured, like a CAFO, then you can get everything out of it, and you get multiple benefits from it. So there are trade-offs in this in terms of the pee management. Yeah, and you're right. I agree.
Other questions? All right.
Ed Weinberg, S3 Consulting. Nice talk, Bruce. So I have a dietary question, which I'll do quickly because maybe it'll be more appropriate for lunchtime. But I'm on a mission to look at foods that are highest in added phosphates, like sodium phosphate or a calcium phosphate. Now, wouldn't that make a great target for recovery and even just keeping it out of the food chain?
Yeah.
So the USDA has set up 2030 champions for food waste. Well, if we look at added phosphate as indeed a waste, is ASU or any of your aligned members in SPA working with these food champions to maybe look at phosphorus in the food chain?
So the one example I know would be like soft drinks, right? They have a lot of added phosphorus as a buffer in there. So are there other ones? I really don't know what the other ones are.
Meat preservatives.
Meat preservatives.
Yeah,
Okay, yeah.
And
Yeah.
I'm thinking cereal too.
Yeah.
So I've got a little home hobby collection of all my Cheerio finds in an empty.
Really?
Yes. And if you treat it as phosphate rock, even though it's not nearly as concentrated in phosphorus, but it doesn't have calcium, fluorides, and radioactivity, maybe that's another target for putting on your map.
Yeah. I hadn't thought about that. That's a really good point. Yeah.
So my second question or comment is, you're talking about your origins with NSF and RCN, which I believe was a 5-year grant program. So has basically expired. Well, NSF has moved on to their 10 big ideas to look at big data and converging research to face societal challenges. I can't think of a more greater societal challenge than our phosphorus problem. So
Yeah.
I'd like to pose to you, and I hope to talk to Jim and Rebecca after the session to talk about how you can reemerge into the NSF program of big ideas and further expand on your phosphorus recovery work.
Yeah, interestingly on that line, I was talking last night with Carl Rockney, who's the NSF program manager, and we were talking about essentially the exact same idea. He's very eager about this. One of the interesting things that we concluded in our discussion last night was that if you take this path, you really need to combine phosphorus and nitrogen together because they go together. If you put the two together, then you get much more of the whole package, and it'll probably, one, address the issue better and also sell better. Yeah.
You know, and that's a good point, but you know, I get this perturbed because I actually did that for USDA SBIR phase 1 proposal, both phosphorus and nitrogen, and the comments back were, oh well, you're doing too much. Why don't you do one versus the other?
Okay, so but Carl just did one internal thing within NSF, and it was just on nitrogen. The comment was, it's not big enough, it's too narrow. Okay, so, all right, so there's a lot of internal inconsistencies within the NSF. But anyway, so that thing spurred our discussion. Okay. No,
We have a question from Ahmed here.
yeah.
Bruce, thank you very much for distilling all that knowledge from the RCN into such good takeaways here. Just an observation here. We are trying to minimize the mined phosphorus. So for those countries that depend on phosphorus, the mined phosphorus, what's the value proposition for them to reduce it?
Well, okay, so what you have to understand here is that we're still using phosphorus, but it's now recycling. Okay, so instead of just once through system, now you've got a circular economy on phosphorus. So if I were a mining company or a mining and fertilizer company, I'd start thinking about some new sources of inputs. It's not just the mines, but it's now these other things that are coming through the system. And so I don't really see a problem with this. It's just another source, and maybe in some cases even better source or an easier source. So, but that's the mindset you have to take, is that you're now going to have multiple sources. There's one. Go ahead. Here, go ahead. Wait a second.
To your point about how intersectional the nitrogen and phosphorus issues are, when it comes to the diet, if we're all to become, half of us, vegetarians, that'll severely impact the amount of nitrogen coming through. Have you thought about the benefits to that and also the benefits to the water savings? If we're to, 4 out of 5 flushes are for washing away pee. If we can eliminate those, I think it strengthens your case.
Yeah. Well, I think you're right. And we haven't looked at the nitrogen thing in a quantitative way like we looked at phosphorus, but it's obvious that it's going to be the same trends on it. And I do want to say a little bit about diet. I said in my talk, well, I'm not an expert on diet. Well, actually, that's not 100% true. Actually, I know a lot about diet. And one of the research areas in our center, the Swedish Center for Environmental Biotechnology, is looking at the interactions among the microorganisms that inhabit our intestines and the human host and diet. We have a big study going on that right now. And I've really educated myself a lot about diet on this. And the truth is, the current, what we call Western diet, which has a lot of meat and a lot of processed food, has a really undesirable effect on human health via the microorganisms. And all those processed foods and the meat are absorbed very high up in the digestive system. And what we're doing is we're actually starving the microorganisms that live in our intestines with the modern Western diet. If we went to a more vegetarian, grain-based diet here, we would feed our microorganisms much better, and they'd be in a much better position to help us be healthy. And so I think you would see some ancillary big health benefits if we could shift the diet this way. And of course, it would help a lot with the phosphorus and the nitrogen as well. All right,
Yeah,
the
last
last
then we'll have
one.
coffee.
You have a huge responsibility here.
Well, since we're on the topic of diet, I just want to maybe point out that I think it's generally true that for reducing the nitrogen and phosphorus pollutions, it's helpful to reduce the meat consumption. But on the other hand, I think we also need to be mindful of what are the nitrogen and phosphorus pollution associated with alternatives, such as fruit and vegetables, which are also in a lot of places are very nitrogen and phosphorus use inefficient. And I think that should be also, so that kind of alternatives should be also considered and also addressed.
Yeah, and I don't know all the details, but I do know, for example, the traditional way of growing rice and rice paddies is really heavily nutrient polluting. So that's an example of it, and maybe that needs to be altered too. But that's another dimension. And I think Jim is going to grab the mic from me.
Thank you so much, Bruce. Give him a big hand.